this party started. So last time, what did we do last time? Last time we did a lot of u-sub integrals where we changed the variable, and oftentimes if we got lucky we made it an easier integral. Okay. Today we do more of that, more of the same. We get to practice the same skills, but what we want to do today is focus more on trig integrals. That is, integrals that involve trig functions. And I thought this was a good idea because I think it's too early to jump onto a new subject. I don't have anything new to say per se today, because I didn't want to jump into a whole new subject, and I wanted us to have more time to practice the u-substitutions. So this is perfect. This is sort of an intermediate step. We get to practice more u-subs just applied to trig functions. So we also get to review all our trig identities. Alright, that's it. There's nothing new to learn, just more u-substitutions and trig identities. So let's jump right into it. Before I jump right into it, I want to point your attention to the famous trig identities. So I've posted on the trig page, or probably for the calculus page as well, on chapter 1, chapter 2 summary, these famous trig identities: cofunctions, Pythagoras identities, the sum angle identities, double angle. Make sure you guys have this handy, because we will be making references to it all day long today. Okay? Just wanted to point that out. Alright, let's get started. So let's start off with something really easy. This one, we said it's really a basic one. There's not much to it, so this would be an easy way to start to review here. We're trying to find an function whose derivative is cosine, so that would be sine of t plus a constant. The derivative sine is cosine t. There, you're done. Well, that was too easy. Here's an interesting thing to do. Take all the different powers of a function and see how far you can get. Since cosine x was too easy, or cosine t was too easy, try cosine square and see how far you can get. Now here you get stuck already. A u-substitution may not be the most easy thing to work with right at the moment. You could try various things. You could try u is equal to cosine. Let me think. What could you try? Hold on. You could try you could try put here u is equal to cosine t, but that won't get you anywhere, because then du would be sine, and there's not even any signs there. That seems attractive for about 5 seconds. And you could try u is equal to cosine squared t, and that doesn't seem to go anywhere. So it's fun to try a whole bunch of things that don't work, and then it's fun to try to keep trying until you get something that works. The classical thing that works here is, of course, one of the trig identities, and that one would be found not in this paragraph, but it would be found right in this paragraph right here, the double angle identities. I'm looking at this one right here. It says that the cosine square is equal to 1 plus cosine 2 theta over 2. If we can use that one, what that does, what the most important feature there is that if you look at the power here, the power is 2 and there's no power over here. It has the effect of reducing the power from a square to not a square. That's why that one is incredibly useful. So we're going to apply it right here in our problem. We're going to say forget about all these ideas. We'll go with the identity, and we'll turn this integral into an integral of 1 plus cosine of 2t all over 2 dt. And by the way, this 2 on the bottom, I could pull it out. It's just 1/2 integral of 1 plus cosine 2t dt. And now I've got something much more manageable, because this is the sum, and when I have the sum I can distribute the integral and do each piece separately. And that's exactly what I intend to do. So I will do that as 1/2 the antiderivative of 1 is t with respect to t, plus the antiderivative of cosine 2t. Well, that would be 1/2 sine of 2t. And that's because I've done a lot of homework and I'm good with my u-subs. This would be a simple u-sub. And of course I've got a c here, plus a constant. That's it. The derivative of sine is cosine. some of you may be stuck on this step here. Maybe it's best if I explain it one more time here. I'll make some little room here and I'll do this in red. The integral of cosine 2t dt. So here I would make a u substitution. I'd say let u is equal to 2t, then du is equal to 2 dt. And this would be a half du is equal to dt. So this dt is that dt and can be exchanged for half du. So this becomes cosine u du with a half on it that can be pulled outside. So that's why this becomes I think I told you guys this before. I said, hey, even if that's a 2 or a 5 or a 7, the pattern is really, really easy. All you do is do the 1/2 sine of 2t. So I said the pattern was like this. If this was a 7, this would be a 1/7 sine 7t. If this was a 5, that would be a 1/5 sine 5t, etc., etc. Anyways, those steps they would go right in here. But I probably won't always do this. I think I'm going to expect that you guys have been doing the homework and you guys are good with this. For cosine 2t, it should be sort of a basic one. Alright. Anyways, that's that. Cosine square, super famous. Somebody knows how to integrate this, they know this famous identity. There's a famous one that goes along with that one. That would be the sine square t, and you would use a similar identity, except instead of having a plus here, you have a minus. Perhaps we'll do that one later. Alright, cosine square was so fun. Why don't we try cosine to the third? Huh? Each one has a brand new challenge. That's what's nice about these. You think you know with the square, you think just because we did the square we can do the third one? Could be a totally different animal altogether. Each one offers a really novel and fresh challenge, more or less. Some of them have the same patterns, but a lot of times they're different. Alright, so this is a classic way to do this one. Here's a classic way to do it. A classic way to do this is you approach it this way. You say, you know what, I've got cosine to the third. That's the same thing as cosine squared times a cosine t times a dt. That is a cosine to the third times another cosine. Sorry, cosine squared times another cosine. It's the same thing as 3 cosines. But the advantage here is that you think about this. What you're doing is you're earmarking one of the cosines. You're setting it aside and say, you know what, I'm going to earmark that precisely for my. That's going to be my du. My du is going to be my cosine t dt. If that's the case, well, what would my u be? Well, u would have to be sine, but this doesn't look like a sine, but it's easily convertible to a sine. Again, if you remember our famous trig identities, where is our famous trig identities? That would be the Pythagorean. You see, you have sine square plus cosine square equals 1, so every cosine square right here can be exchanged for 1 minus the sine square. So that's exactly what we'll do. Come back here. And I'll exchange that, and this will become integral. Here's my exchange. I'll say this cosine t dt. This is earmarked to be the du. This will go 1 minus sine squared t. This is the famous Pythagorean identity variation. And now I go with my u sub. I'll make a little u substitution, and I'll say I'm going to make my u be sine t. Then du would be equal to cosine t dt, and that's exactly perfect. That's what I had planned all this time, because this is going to be exactly this right here. It's going to be a du, right? Stop me if I'm lying. You guys can't stop me. You can't stop the hands. The only thing that can stop the hands is the hands. There's no kryptonite. 1 minus u squared times du. And what do you call that now? That would be a basic one. And so we would finish it off with, alright, the integral of 1 with respect to u would be u minus u to the third over 3 plus a constant. And I can convert back using my dictionary. Sine t minus sine to the third t all over 3 plus a constant. Okay, You see that? A super famous idea. The idea is if you've got 3 cosines, this is a super famous idea. This one you can generalize. Earmark one of those cosines, set it aside. And if you earmark one of them, that was an odd number, then you'll have an even number of cosines here. And every even number of cosines can be easily exchanged for an even number of sines using this 1 minus sine square thing. And that will set you up for an easy u-substitution problem. And this pattern can be generalized. If this was another odd number like 5 or 7, 11, any odd number like that, positive odd number, you can play this game. In fact, it might be a good idea to see if we can repeat that precisely that same game here. What we do is we say, alright, this is cosine to the 4th t times cosine t dt, and what we're doing is earmarking this one to be the du. This one I want to exchange for sine, so I'll go 1 minus sine square t, and that's squared because that's to the 4th, so that's cosine square squared, and that would be times cosine t dt. And now look at us. We go with our little dictionary here, famous u sub. We say, hey, you know what, we're going to say u equal to sine t. That would force du to be cosine t dt. And look what this becomes. This becomes the integral of 1 minus u square. Too fast for you? There's a pause button. Can't do that in live lecture, huh? 1 minus u squared du. Too slow for you? Fast forward it. So this becomes 1 minus, let me think, 1 minus 2, too much talking here, plus u to the 4th du. I'm just foiling this, and that becomes an easy one, a very doable one, right? Check all the steps that I did it carefully. I set aside one of the cosines. It's always good to stop and smell the u substitutions. What's the rush? Okay, let me think. I set aside one of the cosines that left 4. That's a cosine square squared. That's perfect. We made the substitution. This is du, straight out du. There's nothing there. 1 over 1 minus u squared. That gives you 1 minus 2 u squared. So that's foiling. And now it's a piece of cake. I'm ready for business. This will become integral of u over 1, that would be u, minus integral of u squared, that's u to the 3rd over 3. Yeah, you guys can't see, nobody's saying anything. How about there? Plus u to the 5 all over 5 plus a constant. And just finally, just make your substitution and you're good to go. This will become sine t minus 2 sine to the 3rd plus 1/5 sine to the 5th t plus a constant. That's it. As easy as it sounds, that's it. And again, the thing to note here is that you can generalize this process. Anytime you've got a 7 here, you can cosine 7, you can always earmark one of those cosines and turn all the other cosines into sines. And the process will repeat. And you can generalize it to other things too. For example, sine to the 3rd, we could play the same game here. I don't know if I want to do this one all together, but I want to get it started. Sine squared t sine t dt, and then I would say I'm going to make my conversion here. This is 1 minus cosine squared t sine t dt, and I'm setting it up for my u sub. If I make u equal cosine, look how nice this works. If I have 1 minus u squared, and what would du be? Du would be negative sine t dt. That's exactly what I have here. Well, I have to add a negative. So this would become, see, this is exactly the same concept, just applied to a different problem. You earmark one of the signs, and you think, well, what's the derivative? The derivative of what is equal to sine? Well, the derivative of cosine. So if you could convert everything else into cosines, a bunch of cosines under the hand, all you have is, and then those cosines would be your u's, and here's your du. See how it works? If you could earmark the du here, and everything else that's under the hand you can turn into u's, you're set to go. Look, I turned all these into u's. 1 minus u squared du. I told you, piece of cake now. I'll let you guys finish that. That's boring. Alright, let's go on to different idea. Same concept here. Look. This looks incredibly difficult. 3 plus 5 tangent t minus 12 tangent to the 7th t secant squared t. This looks crazy. Any mortal would start crying as soon as they see this. That's unless they understand the principle we just talked about. The principle of earmarking something to be your du. Think about it. If that is the earmarked piece that's going to be the du, what would the u be? If I could make a little dictionary that has u as tangent t, then du would be equal to secant squared t dt. This right here would be the same thing as a du, and I'd be in business. So long as under the hand there's no h's or k's or whatever, so long as under the hand all I have is a bunch of u's. If I have a bunch of u's here and du here, it's all over. See the concept? Alright, if you don't see it, you got to practice a lot. Or maybe rewatch this video many times and practice a lot. See, this is going to work out nicely. I'm going to have 3 plus 5u minus 12u to the 7th. See that? Nothing but u's and constants. And outside, nothing but du. That's beautiful. Such a scary looking problem, but there's nothing to it. All along you had this du earmarked over here, so long as you could convert all these to just plain u's or constant times u's. And it works out nicely. I'll just finish it real quickly. This would be 3u plus 5u squared over 2. Whoa. I'll just finish it real quickly correctly. 3u, no more integral, plus 5u squared over 2 plus negative 12u to the 8 over 8 plus a constant. And then substitute back your tangent for u's and you're done. Okay? Final answer would be 3 tangent t plus 5 halves tangent square t minus 12 over 8 tangent to the 8 t plus c. Capiche? Nice, huh? It's not that bad. Alright, so we did cosine square and cosine to the third and cosine to the first. Next natural thing is, what about cosine to the fourth? And again, here you start to see some patterns. They actually don't offer any new challenges. Sometimes they do and sometimes they don't. It's just the way it goes. This one, I don't think it offers new challenges because we could solve it using the same ideas that we had before. Cosine t dt, we will use that same identity that said this is equal to 1 plus cosine of 2t, of course this is square, all over 2 square dt. There's no calculus from here to here. From here to here, it's just trig identity, one of the famous trig identities. Again, the one I pointed out earlier, I believe it's not that one. Where is my trig identity? Right here. This is the one I'm using over and over again. It works really well when you have even numbers, because you can every even number you can't set aside one of them and you turn the other ones into sine, because you'll have an odd number of them left. That's why this is sort of a better strategy for these. Of course, you may have to do it a couple of times, because look what we've got now. You got this square here. I'll just do a little cleanup on the algebra here. This 1/2, I'll pull it out, but it's square, so I'll pull out a 1/4. That would be integral of, and this has to be FOIL, so it'd be 1 plus 2 cosine 2t plus a cosine square 2t dt. You think, whoa, what a miss. Yeah, it looks like a miss, but it's not that bad, because you can separate this into 3 little problems. This problem is easy. The integral of 1, that would just be t. This one is doable. This is just a u sub. That would be the integral of cosine 2. I'm not even worrying about it. I'm covering it because it's not even a problem. The integral of cosine would be a sine 2t times a half. We've done this one earlier today. And this one, you got another cosine square. How are you going to deal with a cosine square? Well, the same. We've already dealt with cosine square. You use exactly the same identity. Again, that's why I said you may have to use it a couple times. Let me go ahead and clean that up just before I do my final integration. So I want to get rid of that square. The perfect medicine for getting that square is again that identity. So I'll use it here, and it will go like this. Ready? So this will be, that's equal to that, that's equal to that. Let me see what this would be equal to. Yeah, we're gonna need more room. Let's go with 1/4 integral of 1 plus 2 cosine 2t. Well, here we go. This is the part I'm going to expand using my identity. This will be 1/2 1 plus cosine. You double the angle, so it's 4t. And I have the 1/2 there. And of course, all that is times my dt. Let's clean it up some more. This would be 1/4. Let me clean it up. I got 1 plus a half here. That would be 3/2. Plus this one, this would be 2 cosine 2t plus a half cosine 4t dt. Now look at how fun. This one now, it looks to me like a very, very doable one, because the 3/2 it'll be super easy. That's basic. It'll be 3/2 t. The cosine 2t, it'll be easy. That's just the sine 2t with a 1/2 on it. And this one, same thing. It would be a sine 4t with a 1/4 on it. I'm ready to roll on this one. So it'll be 1/4. I'll make some big brackets. Let's go with it. 3/2 t plus 2 times 1/2 sine 2t plus 1/2 1/4 sine 4t plus a constant, whatever. That would clean up as, I distribute that, that would be 3/8 t plus 1/4 sine 2t plus, I got 1/4 here, I'm distributing as 1/4. These two cancel, so 1/4 times that would be 1/16, 1/32 sine 4t plus a constant. And there you go. Fun, huh? The trick, the name of the game? What was the name of the game for this even one? It was to get rid of that 4. Now you can't get rid of that 4 per se immediately, but you can get rid of a 2. So you break it up into little chunks. You get rid of that 2 using the double angle identity. Boom. Then you expand that, and you got another 2 to get rid of. Expand that, and now you just have a basic u-sub after that. That would be at this point right here. No, this point. Stop. Yeah, at this point. That would be just a basic u-sub. Clear? Pretty easy, huh? How about a sine of 2t? Well, again, I said earlier maybe we might do this. Maybe I'll just do one step. This is easy. Super famous identity. Somebody knows this one. You pull out the 1/2, and all you have is a integral of 1 over cosine 2t dt. And that, my friends, that's duck soup. Right? The integral of 1 is t minus the integral of that would be sine 2t, and then you need a half, and that's it, plus a constant. Or you could write it this way. You could write it as 1/2 t minus 1/4 sine 2t plus a constant. I know it's the 1/2 times a constant, but who cares? There's just some other constant. And that would do it. Okay. But wait, there's more. What about sine to the third? Well, again, this one you would just set it, earmark. You would earmark one of the signs, and then make your u-sub. Convert this one to cosines, and make your u-substitution. You would want u to be equal to cosine t, and then that would make du equal to negative sine t dt. That's what this one is earmarked for, etc., etc., etc. All right, let's move on. Those are boring now. What about tangents? Powers of tangents. That seems like something fun, right? We did tangent before. I think we did it with a u-sub last video. And here we consider, what about tangent square? Again, it's all about the identities. Let me scan those real quickly. Famous trig identities. What does the famous trig identities thing tell us? Right here, I'm looking at this one. I'm going to be looking at this one. Oh, this one tells you how to exchange. It tells you every single tangent square can always be exchanged for a secant square theta minus 1. That's the exchange rate right there. So I'm going to go back up here and do it. So every tangent square can be exchanged for a secant square t minus 1. Now how's that going to help you? Now you've got another problem. You got a secant square. Oh, no. That's not a problem, because I reckon that yeah, this is one of your famous. This is one of the famous. This is my famous version of the famous sheet. The integral of secant is actually famous. Is basic. Sorry, it's a basic one. It's just the tangent. So that's going to be really easy to do. So this will be equal to. Sorry, technical difficulties. The antiderivative of secant, that's basic. That's just tangent t. The antiderivative of 1 would just be t plus a constant. It's that simple. Basic. It's on the basic sheet. Okay. Oh, that was no fun. Let's try tangent to the third. What do you think we could do on this one? Maybe try the earmarking thing? No. Maybe. What if we do it like this? Tangent square t, tangent t dt. Then what? Well, we could certainly exchange that one. That one has a famous exchange rate. It's secant square t minus 1 times tangent t dt. Then we can distribute this to the. So you get secant square t minus times tangent t minus tangent t dt. That was just this tangent being distributed to that and being distributed to that. There's no calculus from here to here or from here to here. Just algebra distributing that. But now what? See, sometimes it's not clear whether you made the problem worse or better. But I think on this one, if you just think about it for a little bit, you realize we've actually made it better, because now we can make secant squared t. Let's see if you guys can see that. Secant squared t tangent t dt minus integral of tangent t dt. And again, what I did is I distributed the integral and distributed the dt, and I broke it up into two problems, hoping that each of those little problems is easier than the original beast that I had to deal with. Now I'm looking at this one. I can already tell you this one's easier because we've done this one. Again, we did it on the last lecture, or I think it was done by u-sub. You put sine or sine over cosine, and you make your u be the cosine, blah blah blah. That one's doable. This one also seems doable because I can earmark the secant square. See, I move the secant square over here and I earmark it to be my du. My tangent will be my u, and it will be an easy one. Right? Talk is cheap, let's do it. I'll do it. I'm going to have to do two separate little substitutions, but I'm not afraid. I'll do one over here. If you guys can see it. No? I'll move it over here. There's my u sub. So this one I'm going to make my u is equal to I'm going to make my u equal to tangent t. That will force du to be equal to secant squared t dt. That's going to go in there. For this one over here, I don't want to use because it'll get too confusing, so I'm going to use something else. I'm going to use what should we use? Let's go with blue. I never tried blue that much. Let's go with blue. Blue. Blau. and we shall, wow, it's fun, huh, watching me play with this. This one I'm going to rewrite as, well, I want to rewrite it as sine over cosine, so I'm going to make my u be equal to cosine t. That would force du to be equal to negative sine t dt. That's for this piece right here. But see, I don't want to use u because I've already got u's over here, so the customary thing to do is not to confuse them. Maybe make these w's. Okay? W would be cosine t and dw would be that. And then it would look like this. The integral of secant square dt. I'm looking at the dictionary. That's just a du. And tangent is just tangent. So it'll be u du minus integral. This one will be a sine over a cosine. Sine t dt all over a cosine t. All over a cosine t, let me think, that will be equal to w on the bottom, that's cosine t, and on the top that will be equal to dw with a negative, because I got that negative, so I'll change that to a positive. This will become, I'm ready to roll with it, this will become u squared over 2 plus ln of w plus c, right? But wait, there's more. Making my substitutions back, the u was equal to tangent, so this will become tangent square t all over 2. My w is equal to cosine ln of cosine t plus c. And now I'm done. Phew! Pretty nice, huh? Tangent to the third. You thought it was just some little cheesy little integral, huh? No, it provides lots of fun. Let's go through it again. You separate it, you earmark one of them, but no, you don't earmark. You try to earmark it, but it doesn't work. However, the tangent square can be exchanged for secant square minus 1. You distribute it. Each of these problems becomes easier to handle. On this one, you make a u sub, making u tangent. On this one, you also make a u sub, but you can't mix up too many u's, so you make a w sub. Change of into variable, make a w cosine. dw becomes negative sine. That becomes negative dw, but it has another negative from here, making that positive. Beautiful. Alright, want to try another one? Let's try a couple more. This is the reason I think this one is important is because it's classical. This one is super classical. The integral of secant x, or secant t dt. It's not that easy to do unless you've seen other people do it. And I've seen other people do it. It's a marvelous little trick, but it's a very specialized. And it goes like this. You take your secant t and you multiply by something that's equivalent to 1. Something that's equivalent to 1. And that wouldn't change a thing because all you're doing is multiplying by 1. Well, you don't just write the 1 that way. You write the 1 in the most amazing way you could possibly think about. You write it as secant t plus tangent t all over secant t plus tangent t. Who would have thought that's what would do the trick? Doesn't even look at it. It looks like it. It looks like it's making the problem even worse. This would become secant square t plus secant t tangent t when I distribute this all over secant t plus tangent t dt. And you think to yourself, what a mess. It looked so easy at the beginning and now we've made it incredibly complicated. Yep, that's what most people would say if they've never seen the trick. But here's the marvelous trick for you. You now set up this amazingly crazy u-substitution. You say, hey, I'm going to make a substitution where I'm going to call u equal to secant t plus tangent t. What a crazy thing to do. And then du would be equal to, the derivative of secant would be secant t tangent t Need more room here. The derivative of secant is secant tangent. The derivative of tangent is secant squared t dt. And lo and behold, that's exactly what we have on the numerator. Look at this. What is that on the numerator? That's a secant square plus secant tangent t dt. This is secant square times a secant tangent dt. It's exactly the same thing. On the bottom, look what we have. Secant plus tangent. Secant plus tangent. That's a u. Amazingly, as if by some miracle, this becomes du all over u. I know, huh? It's incredible. It's hard to do that if you've never seen the trick. But now you've seen the trick. This becomes ln of u plus a constant, and you're done. This becomes ln of secant t plus tangent t plus c. Just like that. Very, very nice. Marvelous trick. Specialized trick. Yeah. I wouldn't recommend that you go around multiplying things by secant t plus tangent t. It usually never works. It's very, very specialized for this problem. It works beautifully here, but I am guessing it probably doesn't work anywhere else. So, but I think everybody should see that once in their lifetime. There's a similar one for cosecant. You do this amazing trick where you multiply by cosecant minus cotangent, and just marvelous, beautiful things happen, like magic. I think I posted some questions along that line on the homework or the self quiz for your enjoyment. All right. So I thought maybe we could do a couple more. These are not incredibly important. If you guys want to take a break or come back to this another day, that's okay. It's an option. If you guys got it in you, let's do a couple more. I can do a couple more. You guys should be doing hundreds of these. I can't emphasize how important it is for you guys to become super, super good at integrating. So let's see. Let's make a u sub on this one. I'm gonna go with u is equal to 5 minus cosine t. Yeah, how does that sound? If that's the case, then what would that force du? That would force du to be the derivative of cosine is negative sine, but I've got another negative there, so it would be just sine t dt. And now, what do we have? This becomes the integral of, let me think, sine, cosine, I got nothing. Forget about it. I'm just kidding. Look, it's easy. Let me think, I got a dt. Is it easy? dt, sine t dt, that's right here. So I got a du. I'll forget about the cosine. I will deal with it later. When the hands are ready to deal with the cosine will be there. This will be a du all over u, right? And it almost looks good, except for that part right there, cosine t. If that wasn't there, I'd be in business. So I go back to the dictionary. I ask dictionary, would you please tell me what is a cosine t? The dictionary would answer back, oh, a cosine t could be swung over there. It's 5 minus u, just using algebra. I'll say, okay, I'll take that. And let's see how it goes. This will be 5 minus u all over u du. Now what? Oh, I could break this up into a couple of fractions. This becomes the integral of 5 over u minus u over u du, right? Which indeed becomes something doable. It becomes 1 over u du. That's super famous. That's basic. Minus integral of just 1 du. This is 5 over u, and this u over u becomes 1. So then what? And that becomes 5 ln u minus u, and you're done. So now you substitute back your u's. This would be 5 ln of 5 minus cosine t minus again u was 5 minus cosine t plus a constant. There it is. Nice, huh? See what happens? The glory is for the fearless, for the people who persevere. There's no glory for the people who give up and start crying. Well, there's less glory. Anyways, what about that one? Again, famous ideas from trig. You might want to try to multiply top and bottom by the conjugate. I think the conjugate would be 1 plus cosine t. Yeah, everybody knows how to do this one. Anybody who is somebody has multiplied by the conjugate. 1 minus cosine t, 1 minus cosine t. You don't even know if it's going to give you the right answer or not. You just do it because everybody does it. And see what happens when you multiply by the conjugate. Maybe nothing good will happen. 1 minus cosine t all over 1 minus cosine squared t dt. Well, isn't that nice? The 1 minus cosine t squared can be exchanged for a monomial. Can be exchanged for a sine squared t, as a matter of fact. And the reason that's important, because then you can separate it into a couple of fractions. You can say, well, this becomes 1 over sine t squared dt minus integral of cosine t all over sine squared t dt. And then you say, whoa, 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 whoa. What a crazy mess. So, well, that looks messy, but it's really simple, because the 1 over sine, that is cosecant squared dt, because this is sine squared dt. And what is this, man? This is a cosine over sine and a 1 over sine, right? You can either do this as a u sub, where make your u as sine, and you got the cosine, the du earmarked over here on top. That will work. Make u equal sine, and you'll have 1 over u squared times du. Or you could just recognize it. This is cotangent t, cosecant t dt, and you say, oh, that's basic. That's one of the basic ones. Right here. Isn't it? Told you. See why they pay me? Alright, so let's finish this. Cosecant, that would be cotangent t. And that would be cosecant t plus c. And I believe that changes the sign. That changes the sign. And you're set. Done. Told you. Super famous. Alright, that's enough practice for me.